right, time is up. Pod 1, give me one of these three things that you talked about.
Algebraically, they undo each other when they're
Okay, algebraically, they undo each other. Do you agree with that description?
Yes.
Okay, kind of like e to the natural log of x. They undo each other. Okay, pod 3, give us another one.
Numerically, like a coordinate is going to be opposite.
What do you mean by opposite?
So like the x is going to be in the y spot and the y is going to be in the x.
Okay, x and y switch. Right, so if we have 1, 2, then on the inverse we would have 2, 1. Is that what you mean? Great. Pod 6, can you tell me graphically?
If you have a line, the inverse of that line would be perpendicular. No. Okay, so the slope of a line would be inverse of the slope would be the inverse. No, reciprocal and negative. Something.
Okay. What about like in general, like not just lines?
Something about reciprocal and negative.
She is not here right now. Okay, can anybody help out pod 6? There's a property that inverse graphs have. There's some sort of reflection that takes place.
90 degrees.
Over what? The XY axis.
XY line or whatever that is.
They reflect over the line y equals x. Okay, so we're going to talk about each of these individually. Okay, and then we'll talk about how calculus relates to anything with inverses. Okay, so the first thing, let's talk about algebraically. Algebraically, inverses undo each other. If you remember back to Algebra 2 and pre-calculus, this is how inverses were defined. F of g of x equals x, and g of f of x equals x. Do you remember that? Where you put one function inside of the other, and they should undo each other, so you are just left with x. Okay? I would not write down everything word for word, but at least knowing what I circled, that's what's important up there. When I plug in e to the x into the natural log, they undo each other, and we are left with x because they are inverses of each other. Then let's talk about numerically and graphically both together, okay? Sammy said that from the function to the inverse, the xy coordinates, they're just going to switch from xy to yx, okay? And then Isaac reminded us that our graph reflects across the line y equals x because our x's and y's are switching, okay? So if we have a curve, all right, that has a point AB, then on its inverse we have BA. And as you can see, when we draw the inverse graph, we have that reflection about y equals x. Okay? If you took notes on the warm-up slide, then you have all of this pretty much written down. If you don't, you may want to at least write down that if AB is on F, then BA is on F inverse. Okay? That's going to be important when we get to our calculus work. Okay, let's flash back again to pre-calculus. It is Throwback Thursday, right? Okay, throwback to pre-calculus topic. Okay, algebra 2 topic, how do we determine a graph actually is a function? Say it louder. Vertical line test. Okay, how do we determine a graph has an inverse? Say it. Horizontal line test. Okay. If a graph does not pass the horizontal line test, it does not have an inverse. Okay. Last year when we talked about this, we talked about parabolas. Okay. How many times does a horizontal line pass through this parabola? Twice. It doesn't pass the horizontal line test. If we reflect this about the line y equals x, we get a sideways parabola. And what's wrong with that? It's not a function. Okay? So, a graph must pass the horizontal line test and the vertical line test if we want the inverse to exist. Okay? So, let me ask you this. Would that pass the horizontal line test? Would this one? Was that confusing? Sorry. That is a horrible. We're going to try that again. Does this pass the horizontal line test? Okay. So let's talk about characteristics of these two graphs versus this graph right here. Okay. What happens in this graph? This graph increases, decreases, then increases, right? It changes direction. Do these two graphs change direction? No. Since these two graphs do not change direction, they will pass the horizontal line test. Since this graph changes directions, it's not going to pass the horizontal line test. You see that? All right, so we have a name. So this is what we just talked about, the horizontal line test. If a function passes the vertical line test and the horizontal line test, we call it 1-to-1. That's something that we talked about like that first week of school. Don't worry about writing that down. What's important is this word right here, monotonic. If f is monotonic on its entire domain, then it's 1-to-1, meaning it has an inverse. Monotonic. Anyone care to try to break that word up for me?
Mono.
And what is mono usually stand for? Okay, not that. One. Okay. Tonic. Okay. So here's what I'll tell you. Monotonic, like the one in monotonic, means we're only going one direction. So we're either always increasing or always decreasing. If we change directions, right, we're not going to have an inverse. If a function is monotonic, meaning always increasing or always decreasing, we will have an inverse. So let me ask you this. You can talk about it with your time. Is there a way for us, using calculus, to determine if a function is always decreasing or always increasing. Talk about it with your body. Is there a way for us using calculus to figure this out? And what would that be? Or just say yes or no? All right, anyone brave enough to share their idea? What about Isaac was the one talking, right?
No, it was him.
Isaac, what was your idea?
It was his idea.
What, and what was it?
What was his idea?
He bounced his idea.
Okay, I just need to know it.
He said that we can make like a graph, the derivative graph, and then if it's zero, that means it's just a direction.
Okay, so a derivative can tell us if we're increasing or decreasing, right? If a derivative hits zero, hits the x-axis, we know it's changing directions. Okay, increasing means what about our derivative? Okay, if our derivative is positive, then we are increasing. If our derivative is negative, then we are decreasing. Okay, so if we can determine that our derivative is always positive or that our derivative is always negative, then we know that it's monotonic. So here's our first example. Okay. Now, some of us can tell without calculus what's going to happen. Michael, what's our derivative?
2x plus 2.
Okay. 2x plus 2. Is that always positive or always negative? Is it always positive, always negative, or neither? Who said neither back there?
Isaac.
Why, Cole?
Oh, Isaac said.
And I'm asking you why.
I mean, you could. I mean, I guess you could classify the slope as positive or negative. Like if
What does 2x plus 2 look like?
up to slope is 2. So you can say.
Is that derivative always positive? Is that derivative always negative? Okay? Here, this means we have a negative derivative. Here we have a positive derivative. This is not monotonic. Therefore, our inverse doesn't exist. Okay. Let's go back to what we talked about a couple slides ago. What is this graph? The parabola. Will parabolas ever have an inverse?
No.
No. Half of the parabola will have an inverse, but not an entire parabola. Okay. Second example, does x cubed plus x plus 1 have an inverse? Okay. Now remember, some cubics change directions, some cubics do not. So this isn't as simple as just looking at the equation. Let's use some calculus. Jake, what's our derivative?
3x squared plus 1.
3x squared plus 1. Can we say that that's always positive? Can we say that it's always negative? Or is it positive and negative sometimes? Okay, what's your rationale, Austin, for this always being positive?
I just simply plug in a -1 into x, so we get a positive value.
Okay, what happens anytime you plug in a number into x squared? Positive times a positive number plus 1. This is always, always, always going to be bigger than 0, which means it's monotonic. So, f of x has an inverse. I'll just have you set it right here for now, and then I'll move it where. Got it? Okay. So now for the fun stuff. The derivative of an inverse. This is what's most important about today. Write it down. You know that pop quiz I gave you the other day?
Yeah.
I could throw this on there. This is a rule you need to know.
So we need to remember all those formulas, what we did.
I think I told you all
Are we gonna get our quizzes back today?
that. Are you going to? You think?
It's the one.
Okay, I'm gonna go through why this is the derivative. So it's kind of like a proof. Don't feel like you need to write it down, but some of you like knowing where these things come from, so I'm gonna show you. Okay, so why is this? Okay, we talked about earlier that if you plug an inverse into its function, they undo each other and you're left with x, correct? Okay. Well, let's take the derivative of both sides. Okay. What are we going to have to use to take the derivative of f inverse?
Oh man.
Chain rule, right? Derivative of the outside, leave the inside alone, times the derivative of the inside. Okay, so f inverse prime equals, what's the derivative of x? 1. Okay, so this is what we're looking for, right? F inverse prime of x is 1. We can divide this over f prime of f inverse of x. Okay. All right. So, how do we use this rule? Are you ready? Before we do the problem, we're going to switch it up. The tallest and shortest person in each pod need to stand up and find a new seat. You have 30 seconds. Go.
I think it's
Your blood moving a little bit. Nope, not a permanent thing. You'll be back. Take your notes. Pod 7's not allowed. Pod 7's not allowed. All right, here's our first example. Okay. I'm going to write our rule here at the top. F inverse prime of x is 1 over f prime of f inverse. Okay. So, first of all, we need two things here. Okay? We know that we're going to need to plug a number into f prime, right? We're going to need f inverse of 3 to plug into f prime, and we're actually going to need to know what f inverse of 3 is. Okay? So we need to find first, what is f inverse of 3? How can we figure that out? How can we figure out what f inverse of 3 is? Can our function help us? Okay, if 3 is the x value for our inverse, then 3 is what for our function? Y. So we need to know when 1/4 x cubed plus x minus 1 equals 3. Okay? Since this is a cubic function, this is not something that we can factor. So my advice to you is to play around with some numbers, maybe use your calculator if you need to, but we need to figure out what number do we plug in for x to that function to get 3. Huh? 2, let's try 2. What's 2 cubed? Times 1/4? Plus 2? Minus 1.
I just smarter.
Okay, so f of 2 is 3. You can either guess and check or use your calculator. Sometimes it'll be a problem that you can actually like factor, but this one we kind of didn't have a choice but to guess and check. Okay, so if f of 2 is 3, then that means f inverse of 3 equals 2. Alright, so we can come back over here. We know that f inverse prime of x is 1 over f prime of, we have now determined that f inverse of 3 is 2. So now we need f prime of 2. Okay. So Josie, what's f prime of x?
3, 4, x squared plus 1.
Good. So f prime of 2 would be what?
Oh, wait, 4.
4?
4.
So f inverse prime of 3 is 1 over 4. We had to figure out what the inverse value was, so then we can plug it into our derivative. Of course, all in that denominator, 1 over f prime of f inverse. Okay. I think we should do another problem. What do you think? Yes? Yeah? Okay, but before we do that, anyone wearing red, green, or blue has to move to a different seat. You're wearing all of them. You're wearing red and blue. New pod.
Huh?
All right, once you get to your new seat, here is our next problem. There you have it.
No, I have to. So when we have a quiz over this stuff for now.
No. You still have your gold sheet, right? Okay. All right. What's nice about this problem? They gave us the coordinates and everything. That was nice of them. Okay. Last time we had to figure out the coordinate, right? This time they gave us the coordinate. Okay. So 7, 1. 7, 1 is on which graph? The inverse or the function? Okay. Can you help Q out? As you read this, find the derivative of f inverse at 7, 1. Or f of x is blah, 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 blah. Is 7, 1 on the inverse of the function? Say louder.
Inverse.
It's on the inverse. Okay. So, what does that mean about the function? What coordinate are we looking at for the function?
1, 7. AB.
Okay. All right, so let's write our rule. F inverse of x equals 1 over prime, f prime of f inverse. Okay, so there's our rule. So if we are finding the derivative of the inverse at 7, and this is what we need. 1 over the derivative evaluated at f inverse of 7. Okay, what's f inverse of 7? If our x value is 7, what is our y value for the inverse? 1. Okay, so now we have f inverse prime of 7 is 1 over f prime of 1. Okay, we didn't even need to know anything about 1, 7. Okay, it gave us the y value, so we can plug it in. Now, what do we need? In order to finish this out, we need to find f prime. Okay. This should be fun, right? F prime of x. Okay. Derivative of 7x cubed. 21x squared. Plus, what are we going to have to do for the second part? Chain rule. Okay. So, first we have 3 natural log of x squared times 1 over x. Sorry, I had to write it kind of small. Okay. Now, the nice thing is we're plugging a number. So we don't need to worry about rewriting, making it look pretty, because we're just going to plug a number in anyway. We need f prime of 1. Okay. So f prime of 1 is 21 plus, what's the natural log of 1? Say louder. Natural log of 1. 0. Probably know that. Natural log of 1 is 0. So f prime of 1 is 21. So f inverse prime of 7 is 1 over 21. Okay, I'm going to have you do an example without my guidance, but before you do that, whoever has the longest hair and whoever has the shortest hair at your pod, stand up, find a new seat out of a different pod. Larry's moving no matter what.
Yep. Why does Larry have short hair? You have the longest hair.
All right, so now, you and the people that you were sitting with, I want you to work on this one. You don't know each other, introduce yourself.
My name's Cole. I like long walks on the beach. I like lemon ice cream.
So, yeah. No, you're good. So now we need to figure out what okay. Based on this information right here, what's f inverse a? Okay, so write this as f.
Okay, that's
We're actually finding when I say f inverse prime of x,
yes, just -1. Yes. Ooh.
so x y equals 2.
No. X. 0. What's x squared? 0 squared.
2 is our x y
I'm sorry, I was going to say bit. That's what we do. It's -1. So, it's f inverse prime of 2 equals the only reason I didn't do this is there's no were you guys the problem?
Are you sure it's not, no, yeah,
93. It's negative 1. Is it -3, 0 squared?
All right.
That's negative
Those of you sitting right
of
here.
2 equals.
What did you get?
Goes to the denominator.
All right. These lovely ladies in pod 4 got -1 for an answer. Do you agree?
Yes.
Anyone need to go through that?
Yeah,
Yes?
just the last part.
Okay. Well, we know that we want f inverse prime of 2, which means we need 1 over f prime of f inverse of 2, right? Q, what's f inverse of 2?
-4.
What's f inverse of 2? What's the y value when x is 2 for our inverse?
0.
0. So this we replace with 0. Then we find our derivative, which is -1 minus 3x squared. Right?
Mhm.
And so then we can plug 0 into there. Get -1. So now we have 1 over -1.
I have the right answer, and I'm like, couple of steps,
That's what I got.
I have like one step where I got -4, and I did f prime -4.
How'd you get negative?
I plugged in 2 f inverse. I don't know.
Oh, you plugged into?
To the original.
Oh, is that this thing?
Oh, okay.
Oh, it's always-
Yeah, so since they gave us the point, that made this step really easy.
Okay,
Does
so
that
I
make
just did one
sense?
extra step,
Mhm.
and it doesn't matter.
Okay. If they give you the coordinate for your inverse, they're telling you the y values for right here. If they only give you the x, like in our first example, we had to go find the y value. Okay? So, if they give you the coordinate, that's what you want. That saves you some work. Okay? All right, you can go back to your seat. Your gold sheet has your homework and the agenda for the rest of Unit 2.
Mind your seat.
What time do you?
Yeah.